Hi, welcome to Math 111, our first video lecture. My name is Anne-Marie Harden and I am your instructor for this course. I'm going to give you my screen and we are going to talk about the Cartesian coordinate plane, which happens to be the topic of the first section of our first chapter. So, one of the things we're going to do in this class, as we learn more about functions and how they help us interact with the mathematics we're going to be learning about, is we're going to draw pretty pictures. And we're going to draw pretty pictures on something called the Cartesian coordinate plane. You've probably seen this before. In fact, I'm certain most of you have. The Cartesian coordinate plane is made up of two number lines. One of them, let me get my laser pointer here. One of these number lines is oriented as usual. It's just laid down with 0 in the middle, negative numbers on the left, positive numbers on the right. The other number line is tipped up and kind of stood on its feet. That's this vertical one. And this one, and we orient these two number lines so that they're 0 points across. Okay. So the 0 on the horizontal number line and the 0 on the one we've tipped up on its head, well, stood on its feet, are touching, we're crossing the point. Positive numbers are on top, negative numbers are on bottom. Now, in order to differentiate these, we give them names. We call the one that's normal, that's laid down flat, the x-axis. And the number line that we stood up on its feet, we call that one the y-axis. Now, let's think about how we orient ourselves on this plane. We've got two number lines, each of which has a name. If we talk about how far over we are one way or another on the x-axis, that'll tell us how far we are from our crossing point. We call our crossing point the origin. So this point in the middle is called the origin. So if we move over to the right 2 points, that means we're at 2 on the x-axis. We can talk about the same sort of thing on the y-axis. And if we start at the origin and we go down 4 units, then we're at -4 on the y-axis. If we think about drawing an imaginary line from some point on the plane, so we can talk about this point in terms of how far over it is from the origin and how far down it is from the origin. The over, so this point right here, for example, we can see is in line with the 2 on the x-axis. So we say the x-coordinate of this point is 2. This point is also in line with -4 on the y-axis. So we say the y-coordinate of this point is -4. Now, if we think about these coordinates as being in order, almost like it's a word, right? We know that at, the word AT, is different than ta, the word TA. So think about this in alphabetical order. X comes before Y. So we can specify this point to be at the point 2, -4. Now, mathematics is a language, and so the details matter. These parentheses around these two numbers are important. They tell us that those two numbers form what we call an ordered pair, meaning they describe a point in space. In this case, they describe this point right here. They describe the point 2, -4. Okay, so I want you to take a piece of graph paper, or you can do this on just a regular old piece of paper. I want you to make yourself an X and Y axis. And I want you to graph these points. You may get tripped up by a couple of them. For example, 5/2 is fraction. It's 2.5. You just go halfway between the 2 and the 3. Negative 5.8 is almost to negative 6. Okay? So, graph all these points. Pause this presentation, or at least think about how you would graph them. And this is actually what it looks like. So, make sure you can do this. The point 5.8 is up here. Here's the point negative 5/2, 3. You can see that the x-coordinate is partway between negative 2 and negative 3. Here's the point negative 5.8, negative 3. You can see that the x-coordinate is almost to negative 6. And the y-coordinate is lined up with the negative 3. Okay? This point 0, 0 is the origin. It's very important. That's why we call it O. The rest of them are just labeled so we can differentiate them. Okay? If this bothers you, if you have any troubles with this, please, 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 please ask the question, because this is absolutely foundational. X always comes first, and X's are picked up from the horizontal x-axis. Okay. So some important facts about the Cartesian coordinate plane. This first one seems is kind of a funny way of saying that if the coordinates are the same and in the same order, and they have to be the same number and in the same order, then we are looking at the same point. It's the only way that we're looking at the same point is if A equals C, in other words, if our x coordinates are the same, and if B equals D, in other words, if our y coordinates are the same. This one's an important one. We're going to talk a lot about what we call x-intercepts. X-intercepts are sometimes also called zeros. And sometimes they're called roots. And the reason for that is that y equals 0 everywhere on the x-axis. And the x-axis is very important, because if we're trying to find x-intercepts, those are the points where the graph of a function, we'll talk a lot more about this in a little bit, so don't worry about it too much. But what I need you to know is that any point on the x-axis has got a y-coordinate of 0. That is by definition. There is no getting away from it. If we are looking for the x-intercept, y equals 0. Because every point on the x-axis has a y-coordinate of 0. Now, there's something similar for what we call the y-intercepts. And the y-intercepts are for the graph of the function across the y-axis. And again, this is kind of similar to the previous one, but every single point on the y-axis has an x-coordinate that is 0. So if we are looking for y-intercepts, and we will do this, we need to set our x's to 0. That is the definition. I've already talked about the origin, point 0, 0. It is the only point that is common to both the x and the y-axis. Okay, we talk about quadrants over here, and we start in the positive x. If we start in the portion of the region where both x and y are positive, that's this upper right-hand corner. You might think of it as the northeast corner. This is quadrant 1. In quadrant 1, both x and y are greater than 0. And then we move counterclockwise. So we'll move over here. Quadrant 2. Now notice what's happened here. In this quadrant, every point will have a negative x-coordinate and a positive y-coordinate. Move to quadrant 3. In quadrant 3, both the x-coordinates and the y-coordinates are negative. And then quadrant 4, the The x-coordinate is again positive, but the y-coordinate is now negative. I just want you to know which quadrant is which, so that we can talk about our regions in space. So we start here in the upper left to upper right-hand corner, and we move counterclockwise, quadrant 1, 2, 3, and 4. Okay, symmetry is an important notion that we're going to talk about more when we start talking about functions. But think of a symmetry, a line of symmetry, as a mirror. And if you can put a mirror down between 2 points and one of them would reflect right back over onto the other one, then the points are symmetrical about that line. The other way you can think about this is if you've got a Cartesian coordinate plane on a piece of paper and you fold that plane along a line and you hold it up to the light, if your 2 points would lie right on top of one another, then they are symmetrical across that line. And there are tests we can do for symmetry. So we can test for symmetry about the x-axis. And the way that we test that is we look to see if their x coordinates are equal. And we'll take a look at some examples here in a minute. If their x coordinates are equal, then they might be symmetrical about the x-axis. Maybe. The next thing we look to do is we look to see if their y coordinates are equal in absolute value, but opposite in sign. What that means is they've got the same number, like 3, but one of them is positive and one of them is negative. One would be -3, one would be -3. So for example, let's look at the points 3, 2 and 3, -2. First thing we check, if we're checking for symmetry about the x-axis, the first thing we check to see is if their x coordinates are equal. In this case, they are. Then we look to see if their y coordinates are equal in value, in magnitude, but opposite in sign. And we've got a 2 and a -2. So yes, they are. So these 2 points are symmetric about the x-axis. We've got another example here. Make sure you understand why these 2 points, 2, 1/5, or -2, 1/5, and -2, -1/5, are symmetrical about the x-axis. Okay, now we can also talk about symmetry about the y-axis. And when we're talking about symmetry about the y-axis, that would be like if we took our piece of paper and we folded it along the y-axis and we look to see if 2 points line up on one another. If we think for a minute about what that means, it means that their y coordinates are going to have to be equal. So we say B equals D, because we're talking about the points A, B, and C, D. And their x coordinates would have to be equal in value, but opposite in sign. In other words, they're equally spaced away from the y-axis, because their x values are centered. The y-axis is centered between them, is what we're talking about. So let's look at these 2 points, 7, 3 and -7, 3. First thing we check is we check to see if their x values are equal. They're not equal. But then we check to see but they're almost equal. They're equal but opposite. So, okay, maybe we're symmetrical about the y-axis. Then we look at the y coordinates. They are equal. So we remember that if 2 points have got x coordinates that are equal in value but opposite in sign, and their y coordinates are equal, then those 2 points are symmetrical about the y-axis. Right. Now, we can also talk about symmetry about the origin. And this is kind of like folding your paper in quarters. So our points are equally centered away from the origin. The origin is centered between them. And it doesn't take you too long to figure out that this is kind of a combination of both being symmetrical about the x-axis and the y-axis. And what it means is that our x coordinates are equal in value but opposite in sign, and our y coordinates are equal in value and opposite in sign, like these points down here. Here's some examples. Q and R are symmetrical about the x-axis. P and S are symmetrical about the x-axis. P and Q are symmetrical about the y-axis. And R and S are symmetrical about the y-axis. P and R, this one and this one, are symmetrical across the origin. See how the origin is centered between these 2 points? And Q and S are symmetrical about the origin. Okay. So let's do an example. And I want you to pause this video and I want you to work through this. See if you can get it before you look at the answer I'm going to put up in a minute. So we're going to take the point, -2, 3, and we want to write down the points that are symmetrical to this point about the x-axis, the y-axis, and the origin. Okay, pause the video and write down your answers. I'm going to put up the solution now. So if we took our point P about the x-axis, we remember that that means that the x-coordinates have to be equal and the y-coordinates are equal in value but opposite in sign. So this point right here, -2, -3 is the point that is symmetrical about the x-axis with respect to P. Let's talk about symmetry about the y-axis. Symmetry about the y-axis, we remember, means their x values have to be equal in value but opposite in sign, and their y values of the points have to be equal, like the point 2, 3. And if we want to talk about symmetry about the origin, we just reverse the signs on both coordinates, and we get down here to 2, -3. All right. This is an important concept. Make sure this makes sense to you. If it doesn't, ask me the questions. All right, the other thing we're going to do, and this is going to carry through to future classes, and it's really actually pretty fundamental, is we're going to talk about how we calculate the distance between 2 points in the plane. And now, this formula looks daunting, but it's based on the Pythagorean theorem. So let's talk about 2 points. A point here, point 1, is at some point in space. We're just going to call that x1, y1. And we care about the distance between this point P and another point Q. That is at some other point in space. We're just going to call those coordinates x2 and y2. It doesn't matter what they are. These are just placeholders for numbers we'll talk about in a minute. Now I want to drop a vertical line from this upper point. Just drop it straight down. Remember that every point on that vertical line has the same x-coordinate. In this case, that's going to have x coordinate that is x2, same as the top line. From the lower line, the point P in this example, I'm going to draw a line that's horizontal straight across. Now this point will have coordinates x2 and y1. Remember your Pythagorean theorem. The Pythagorean theorem says that the length of that line right there, the length of this line, this horizontal line, squared, plus the length of this vertical line, squared, is equal to the length of the hypotenuse, squared. We talk about that usually as a squared plus b squared equals c squared. Now, the distance, the length of this horizontal line, you've seen this before, it's what we call the run between these 2 points, but it's the difference between x2 and x1. That's what this is. This is the length of the horizontal line. And take this length and we're going to square it. Now the length of the vertical leg is just the difference in y coordinates. y2 minus y1. And we're going to square this. We add these two together, and that equals the square of our distance. Now what we really care about is the actual distance. So we're going to take the square root. Now this may look a lot to you like the slope formula. Make sure, and it's similar. It is similar. You've got x2 minus x1, you've got y2 minus y1. But they're not divided. Remember, the slope is a rise over a run, so it's a ratio. This is a different critter. This is based on the Pythagorean theorem. And what this says is that the distance between any 2 points can be found by finding the difference in the x-coordinates and squaring that, finding the difference in the y-coordinates, squaring that, adding those two numbers together, and taking the square root. Let's do an example. We're going to find the difference between the points -2, 3, and 1, -3. I'm sorry about the line break there, it got kind of weird. Okay, and here's what we're going to do. We start with the distance formula. D equals x2 minus x1 squared plus y2 minus y1 squared. Now our x's and our y's come from our points. So let's call this guy P1. P is 0.1. So the x-coordinate of P is x1. The y-coordinate of P is y1. We're going to call Q 0.2. So the x-coordinate of 2 is x2. Sorry, the x-coordinate of Q is x2, and the y-coordinate of Q is y2. So now we just plug stuff in. The distance is equal to x2, which is 1, minus x1, which is -2. That difference squared, plus y2, which is -3, minus y1, which is 3. That difference squared. And put it all, add them together and put them under a square root sign. Or 1 minus -2 is 3. Square that, you get 9. Plus -3 minus 3 is -6. So square that, you get 36. So we get the square root of 45. Now you might be tempted to take out your calculator and plug that in. We're not going to do that. We're going to leave these as exact values. And the square root of 45 simplifies to 3 square root of 5. This is something you need to be able to do. You should have learned it in Math 95 or whatever your previous math class was. But just in case, I'm going to adjust my screen a little so I can write on it. Sorry, my picture is going to get kind of weird. But here you go. So we're going to talk about how we get from the square root of 45 to 3 square root of 5. And what we do is we remember, sorry, I just want to do this with my finger. Just trying to make it more legible. My screen doesn't like my stylus. Okay, so the square root of 45. We remember that 45 is 9 times 5. And I picked 9 times 5 because I'm trying to get some number that's a perfect square under there. 9 happens to be a perfect square. And then what I do is I remember that I can separate out products, so only things that are multiplied together, under a square root sign, right? So the square root of 9 times 5 is the same thing as the square root of 9 multiplied by the square root of 5. Do not do this if there's an addition or a subtraction in there. It only works with multiplication or division to separate out, like I've done here. Now, square root of 9 is 3, so this is 3 square root 5. Okay? Make sure you know how to do that. You may need to practice some. It may have been a while. But it's something we really need to do, be able to do in this class. Get back my laser pointer. Okay, so let's talk about how we would find all of the points. That's what that says. All of the points that have an x-coordinate of 1 and are 4 units from this point 3, 2. And I'm going to give you a hint. There will be 2 of them. There's one down here, and there's one up here. So what are we going to do? Well, we're going to use our distance formula. If you think you know how to do this, I do encourage you to go ahead and pause the video and write down what you think is the right way to do this. And then we'll talk, and I'm going to talk through it here in a second. But math is not a spectator sport, and you're going to get the most out of this class if you participate fully, and that means trying some of these examples for yourself. So let's do this one. We start with the distance formula. And distance formula is this thing right here. The distance between any two points in space is given by the difference in the x coordinates squared, added to the difference in the y coordinates squared, and then take the square root of that sum. So in this case, we know my x1 and x2. x1 is 3, x2 is 2. I know that the x coordinate on the points I care about is going to be 1. And I know my distance is 4. Don't know my y2. That's okay. We're going to leave it as a variable. So 4 equals 1 minus 3. This came from the x values, right? Square that number. Plus y minus 2. We don't know the y coordinate, but we know the point we start with. And square that. Add them together, take the square root. Okay. Do a little arithmetic. We get to 4 equals the square root of 4 plus y minus 2 squared. Now, I want to get this y by itself. That means I have to get it out from underneath the square root. And we remember that in order to get things out from under a square root, we square it. Think about it for a minute. So the square root of 3 is 9, right? And 3 squared is 9. So squaring a value undoes the square root, takes it away. So we're going to square both sides of this equation. We get 16 equals 4 plus y minus 2 squared. There's a couple of different ways we can solve this. The easiest thing to do is isolate the squared quantity, and then we can take the square root of both sides of the equation. But we have to remember to take both the positive and the negative roots. So that's what I've got right here. And we end up with the positive and negative square root of 12 equals 2 minus 3. Sorry, y minus 2. Add 2 to both sides, and we get y equals 2 plus or minus the square root of 3. That looks weird, but it is a number. And so this would be one answer. The other one would be up here. Now, if you had to graph that, you would actually figure out the decimal approximation and put a point in about the right spot on the coordinate plane. We aren't going to graph it. We are just going to write that answer right there. Okay? All right. Let's talk for a minute about how we find the point that is halfway between 2 points. This is what we call the midpoint formula. And it's kind of exactly what you would expect. We just find the halfway point between the x's and the halfway point between the y's, and that is the midpoint, the point that is halfway between these two lines. So this point lies on the line that connects these 2 points and is halfway. So this distance is equal to that distance. So let's practice this. Let's find the point that is halfway between, -2, 3 and 1, -3. Plug it into the midpoint formula. The midpoint formula says that the x-coordinate of the point that's halfway in between these 2 points is going to be at the halfway point of the x and at the halfway point of the y's. So again, we define our x1s, y1s, x2s, and y2s. So we'll call point P point 1. So x1 is -2. y1 is 3. x2 is 1. y2 is -3. Midpoint will be at -2 plus 1. That's the sum of the x-coordinates divided by 2, or -1/2. -1/2 is halfway between -2 and 1. And 3 and -3, add those together, you get 0. 0 divided by 2 is still 0. And this point right here, Scott, at -2, 0, is the midpoint between our points of interest, our P and our Q. Okay, we are going to do a few proofs. I know. Proofs are just ways to verify for ourselves that something that someone tells us is true. Someone has told me that 2 points are symmetrical about the y-axis. Or sorry, about the points x equals y. If their x and y coordinates are reversed. That's what this says. This says prove that the points AB and BA are symmetrical about the line y equals x. Okay, so how are we going to go about doing this? Well, let's start with assuming that this statement is true. And if we do that, then we need to remember what our conditions of symmetry are. Our conditions of symmetry are that, and you may not know this, so let me tell you. 2 points are symmetrical about a line if that line passes through the midpoint between those 2 points, and if that line is perpendicular to the line that would connect the 2 points. So let's start with the first one because that's easy. We can find the midpoint of our 2 points using the midpoint formula. So we do that, and we know that x1 we'll call AB point 1 and BA point 2. So x1 is A, x2 is B, y1, sorry, is okay, which one did I, it doesn't matter. 1x is A, 1x is B, 1y is A, 1y is B. We can add maybe order. We see that A plus B over 2 is equal to A plus B over 2. And sure enough, our x and our y coordinates are equal at the midpoint of this line. Now, what's that mean? Well, it means that this midpoint is on the line y equals x. It satisfies that condition, y equals x. Okay. Now, this one's a little harder, and you have to think back a little further. Remember that 2 lines are perpendicular if their slopes are negative reciprocals, right? So first thing we need to do is realize that the slope of the line y equals x is 1. So what we want to do is we want to check and see if the slope of this line between these 2 points is the negative reciprocal of 1. In other words, is that slope negative 1? So if I plug these 2 coordinates into the slope formula, and you should remember the slope formula, you don't go back and look it up for yourself. If we do that, we realize that the slope is equal to a minus b over b minus a. Do a little bit of algebra, and sure enough, we realize that the slope of the line between these 2 points is negative 1. And so the lines are perpendicular. So this situation meets our 2 conditions of symmetry. The line y equals x does pass through the midpoint of the points, and the line between these 2 points is perpendicular to that line. So yeah, somebody was right. They told me the truth. 2 points, we can prove that 2 points are symmetrical about the line y equals x if their x and y coordinates are reversed. Okay, I went through quite a bit of stuff about points and lines in this presentation. I encourage you to ask any questions that you have that are bothering you. I also encourage you to post on the forums if something's bothering you. So you can either reach out to me by email, but I'd really prefer that you post your questions on the class forums so that your classmates can interact, and I can kind of gauge how many people have the same questions, and we will talk through them in class. All right, I will talk to you all, or well, either in class or online, one or the other, depending on a lot of stuff. So I will talk to you all again soon. Have a great day. Do good math. Do a little math every day. All right.